Okay, hello and welcome to a supplemental lecture on compound symmetry and sphericity. The goal of this lecture is to expand a little bit upon some of the material that I presented in one of my regular class lectures, and also to expand upon some of the material that is presented in the text. Compound symmetry and sphericity are complicated concepts. They can be a little bit difficult to understand, and honestly, after spending a fair bit of time looking through different textbooks and websites about statistics, it seemed that there wasn't a very good consistent explanation of how these concepts work that doesn't involve an awful lot of matrix algebra, and which might be a bit beyond the scope of this class. So my hope today in this lecture is to give you a decent sense of how these concepts work, how they are related to one another, and why they're important, without getting too heavy into the details. So hopefully this will be helpful. Where this all comes from is from just the basics of dependent designs, which we are considering in Unit 4 of our class. Now recall, in the case of dependent designs, we have multiple dependent variables. That's different, really, from all the other designs that we've considered in this semester. In almost all cases prior to this, we've had one and only one outcome measure or dependent variable. Here now we have multiple ones. So you might imagine having a participant who's going through some sort, or a group of participants going through some sort of clinical trial. We have measures of their symptom levels at pre-treatment, at post-treatment, and at some sort of follow-up. So these are three separate outcome variables, but what we often like to do is we like to treat them as if they were really, in a sense, one dependent variable. So we might speak about the overall effect of time, or the overall effect of treatment on symptoms. And what we mean is how the pattern of responses change across these multiple variables for the different participants. So we're kind of taking more than two or more dependent or outcome variables, and we're in a sense trying to combine them or treat them as if they were sort of the same thing. Now, this isn't easy to do because, of course, the different outcome variables will be dependent upon one another or correlated with one another because they're coming from the same participants. So someone who scores relatively high on whatever the measure is at pre-treatment will likely score fairly high on whatever the treatment is or whatever the measure is at post-treatment. And someone who scores relatively low will tend to score relatively low. There'll necessarily be kind of a relationship between these different variables. So what we try and do with that is we can make some fairly complex assumptions about the data, which goes to compound symmetry and sphericity, and we can pursue what's called the univariate approach to data analysis. And this is really what we focused on in our class. This is the classic repeated measures way of doing ANOVA. Alternatively, if we want to have multiple dependent variables or outcome variables, we can adopt an entirely different approach to data analysis called the multivariate approach. This is where we treat our repeated measures ANOVA as a MANOVA, as a multiple analysis of variance, which it is, and it's just another way of doing data analysis. It's a way that we've touched upon briefly, but is really beyond the scope of this class. It's something that you would learn in Dr. Troop Gordon's multivariate stats class. So just to characterize how these two ways of thinking about data are different, we can imagine in the univariate approach that we're treating all these scores on these separate outcome variables as if they were all scores on one outcome variable. And here I've got a very small data set for only 5 participants who go through each of them 3 conditions, condition A, B, and C, and they have scores, each person for each of those conditions. And I've stacked them, as you can see, in what's sometimes called a long format for data, where we're repeating ID number 1, 2, 3, 4, 5 for condition A, 1, 2, 3, 4, 5 for condition B, 1, 2, 3, 4, 5 for condition C, to illustrate this idea that we're taking all this separate data and kind of squishing it into one column, treating it like one variable, which we could call score or time or effect or whatever we choose. In contrast to that, the multivariate approach would treat the data as if it was separate outcome variables, which it honestly really is. In a way, the multivariate approach is much more sensible because it treats the data like what it really is, which is to say separate scores on separate variables which may or may not be particularly correlated with one another. So the purpose of these two figures is just to illustrate that difference between the univariate approach and the multivariate approach. So let's focus on this univariate approach first. What are these assumptions that I've mentioned that we have to make? Well, the assumptions are the assumptions of compound symmetry and sphericity, two things that go along together. Now, consider first a single factor or one-way analysis where we have a predictor variable that has 3 levels. So in the case of an independent design, these would be 3 different groups, be different people within each of these groups. In the case of our dependent design, these 3 levels would be 3 different conditions, and we'd have the same people in each condition. So again, one predictor variable or factor, so it's a one-way analysis, and just for the purpose of this discussion, we can imagine a one-way analysis that occurs within an independent design or within a dependent design. And I'm making this comparison to emphasize how these are in some ways similar and in some ways different. And of course, for the purpose of this supplemental lecture, and indeed for the purpose of this unit, we're really interested in how this stuff works for dependent designs. So regardless of whether we're in an independent or a dependent design, we can make a special matrix to describe the relationships between the measures that we make for these different levels. And this matrix is called a population covariance matrix, or sometimes called a variance covariance matrix. The basic idea of this matrix, and by the way, matrix just means a rectangular arrangement of numbers. In this case, these numbers correspond to, on the diagonal, the variances within each group or condition, and on the off diagonal, the covariances between the groups and conditions. So if you look at this image here, we've got, remember, 3 conditions. Going down the diagonal, we have the variance of condition 1, or in a sense, you could say the covariance of condition 1 with itself. Variance of condition 2, going down the diagonal, variance of condition 3, going down the diagonal. And on the off diagonal, we have the covariance, which I've just indicated with the letter alpha here, just because it fit easier than writing cove or covariance. The covariance of condition 1 and condition 2, condition 1 and condition 3, and condition 2 and condition 3. And obviously the matrix has a kind of a reflective symmetry across the diagonal. The numbers above the diagonal are reflecting the numbers below the diagonal. So let's focus on these diagonal elements first, these variances. In the case of both independent and dependent designs, we assume equal variances across groups or conditions. So recall, if we think back to earlier in the semester, we talked about the assumption of homogeneity of variance. If we were doing an independent design, where we had 3 different groups, and these groups were non-overlapping and they're independent of one another, we might ask, is the variance on the outcome variable the same or at least similar in group 1 as in group 2 as in group 3? So that assumption of the similarity between variances holds or is made for both independent and for dependent designs. And just briefly, we can try to remember, why is this important to make this assumption, or to hope that these variances are the same or at least very similar? And by the way, just as a further reminder, in the case of both independent and dependent designs, we assume equal variances in the population, meaning that if we had all the people who could possibly be in group 1 versus group 2 versus group 3, we would assume that the variance on whatever we're measuring is equal in the population. Now we know that in the sample, the variances can and probably will be a little bit different from each other. So we don't absolutely have to see equal variances in our samples, but we'd like to see them variances which are fairly similar. So just a quick reminder there. We say equality of variance or homogeneity of variance. In the samples, we're hoping that they'll be similar. We don't necessarily expect, or we wouldn't expect that they would be exactly the same. Okay, but again, why is this so important to think about? Okay, so let's take a look at our data here. Here is data for our independent design, and here is data for our dependent design. I've arranged the data this way to show that the data, the numbers themselves are the same, and we can kind of arrange them the same way. In the case of the independent design, the column for ID numbers is a little bit confusing. It's just meant to suggest that group score A is for group A containing people or participants 1, 2, 3, 4, and 5. Score B is for group B containing participants 6, 7, 8, and so on. In the case of our dependent design, of course, we only have 5 people, ID numbers 1, 2, 3, 4, 5. Each of those people go through all 3 conditions, so they have scores for each of those conditions. The point, though, here is that what we'd like to see is that the differences between our groups, in the case of our independent design, or our conditions, in the case of our dependent design, those should be due to differences in treatment. That is, differences between what happened to group A versus group B versus group C, or what happened in condition A versus condition B, condition C. We'd like it to be the case that any differences we observe are due to those treatment effects, those manipulations, or those things that we did with these groups or conditions. But that only really makes sense when the variances of those groups or conditions are more or less equal. And that's especially true when group or condition sizes are equal. You could imagine that if the variances for group A or condition A were very different than those for condition B or group B or so on, it would become difficult to determine whether differences between those groups or between those conditions were due to our manipulations or our treatments, or were due to just the fact that these groups have radically different variances. Now that may be a little bit difficult to picture, so allow me to at least try to help you out. Here's a situation in which we have data from 3 different groups or conditions, and you can see that the variances for those groups or conditions are more or less the same. They're the same number of people in each group. By the way, in group or condition B, there are 2 folks who have exactly the same data point, so they're kind of stacked. But trust me, they're the same number of people, 5, in each group or condition, and the variances in each group or condition are about the same. And thus it makes sense to say that, well, there's this effect such that condition A and condition B, group A and group B, don't really differ from each other, but group C is slightly less than group A or B. That kind of makes sense, in part because the variances within these groups or conditions are about the same from one another. So again, just to repeat that point, it makes sense to test differences between means across these groups or conditions, even though there's some overlapping data, just because we know that the variances are about the same. So thus differences in mean level of symptoms or whatever the outcome variable is can be meaningfully talked about. Now in contrast, here is some data from 5 people in each of 3 different conditions if it was a dependent design, or 15 people, 5 in each of 3 conditions if it was an independent design. And here you can see that the variances in these groups are very different. Note that the sizes of the groups are still the same, and even the means are about the same. This is kind of fake data that I made that has almost the same mean for group A, group B, and group C as it did in my previous example where the variances were very similar. All I did here was try and screw up the data such that the variance in group or condition A was very big and the variance in group or condition B was somewhat small. The point of this is that it doesn't make a lot of sense to test differences between the means across these different groups or conditions, because the variances are very, very different. I mean, you could run a repeated measures ANOVA, or if this was dependent design, or if it was an independent design, you could do an ANOVA, but the radical difference in variances might make it really difficult to interpret whether the fact that the mean seems about the same in group A as compared to group B is in a sense is a meaningful conclusion to make, or it's just due to the fact that group A has this very, very wide variance and group B has this very, very narrow variance. So again, this situation here is very hard to work with. The previous situation from my previous slide is a situation that's easier to work with because the variances in the different groups or conditions are about the same. So the important points to make here are that in both independent and dependent designs, we assume equal variances across groups or conditions. And as we've discussed before, ANOVA can be robust to violations in this assumption as long as the sizes of the groups, that is to say the number of people or observations in the groups or conditions, are about equal. And in the case of dependent designs, that's usually the case because you have a group of folks who you put through separate conditions. So there should be the same number of people in condition A and condition B and condition C because they're the same people. You might not have that happen if you have dropout. You know, if you're doing a clinical trial and people are being given a drug or a treatment and they're being followed over time, but by the third wave, by post-test number 2 or whatever, people have dropped out of the study, then you would have unequal sizes in your conditions, and just like with independent designs, you would worry much more about differences in variances across these conditions. It's a little bit beyond the scope right now, but that issue, dropout from designs that are dependent, is a big problem for clinical trials. When you lose subjects from your trial between pre-test and post-test and follow-up, it can really screw up interpretations of clinical trials. Just a side point there. Anyway, so that's the idea, or an idea, about the diagonal element in our matrix. Again, diagonal element referring to variances of the different groups or of the different conditions. Now let's focus on those off-diagonal elements. Remember, these are the covariances between groups in the case of an independent design, the covariance of group A and group B, group A and group C on whatever measure you're making. Or in the case of a dependent design, it's the covariance between condition A and condition B and condition C, so on whatever measurement you're making. Now again, we can ask, why is this important? Why is this an assumption that we want to make, or something that we like to see in our data? Well, consider an independent design. Again, this would be a design in which we have 3 different groups which are non-overlapping, which contain different people. If such a case, we had group A, group B, and group C, and they're being each measured on some variable, and we're looking at differences between those groups, we would expect the covariances between those groups to be 0, at least in the population. In the sample, they might be non-zero, but we'd expect them to be pretty small because, again, each group contains different people. So the score that participant 1 has in group A shouldn't really be in any way related to the score that participant 5 has in group B, because those are, again, different people. If that's a little bit hard to visualize, consider this image here. Again, this is our independent design, and the point that I just tried to make is that ID number person number 1's score shouldn't really have any influence on person number 6's score, or indeed on person number 11's score, because those are different people and they're in different conditions. So as a consequence, the score for group A shouldn't be correlated with the score for group B or group C. Now, in the population, we assume a zero correlation. In our actual sample, for instance, if you were to run covariances using the data that you see in the image right in front of you, you might see that there is some covariance, but we're assuming it's fairly small because, again, these are different people, they're in different conditions. And to that point, the differences between those groups should be due to differences in treatment. That is what we did to one group, group A versus group B versus group C, as well as some individual differences between those participants. Recall that it may be the case that the scores on average in group C are much lower than those in group A and B. That's hopefully due to something that is different in terms of our treatment of group C than group A or B. They got some different medication or they got some sort of different psychotherapy, but it can also have something to do with the fact that maybe there are just individual differences among the people such that those who ended up in group C tended to be naturally lower in whatever measure we're making. So again, to be clear, if we're doing an independent design, we assume that the covariances between the values or scores for our outcome variable in our different groups are zero, or at least very close. Now let's consider a dependent design. Here again, we're looking at the covariances between conditions, condition A and condition B and condition C. Here, we think that the covariances, or we assume that the covariances in the population won't be zero. And even in our sample, they will not be zero. We're not surprised if we see that there's a covariation or a correlation between scores in condition A and condition B, because again, and hopefully this is obvious, they're the same people in each condition. So my score when I'm in condition 1 has some bearing, or condition A has some bearing on my score in condition B and condition C. Yours would too. So again, just to kind of illustrate that point, in a dependent design, we expect that participants who have particularly high scores in one condition will probably have somewhat higher scores in another condition, and people who have particularly low scores in one condition will probably tend to have particularly low scores in the other conditions. That's the idea of the covariation or the correlation. You could imagine this in terms of some sort of a clinical trial where people are being given a treatment for depression, and condition A is before treatment, and condition B is after treatment, and condition C is 1 month follow-up, and the scores are all measures of some depression-related variable. It's just likely going to be the case that if someone is particularly depressed at a time point, or condition A at time point 1 pre-treatment, they're going to be somewhat high on depression at B and at C, even if the treatment itself is effective. And someone who's relatively low in depression will tend to be on the lower end of the scale at the other time points as well. Just to illustrate this, here we have data arranged in a long format again, and we're here expecting that the scores for the different conditions are not independent of one another, because as I've said now a couple different times, person number 1's score in condition A should have some connection to his or her score in condition B and his or her score in condition C. By the way, as I work through these examples and show these images, I hope it's clear or obvious that the numbers, that is, the values for the variable score, are the same in both my example of the independent design and the dependent design. I'm doing that deliberately just to show how you can treat the same numbers in different ways depending on the type of study that you did to yield those numbers, whether the study was an independent design study or a dependent design study. So again, here's our long format data. Here's our kind of more traditional wide format data, and you can see again that we expect there to be some sort of a correlation or a covariation Correlation is just standardized covariation between score for condition A and condition B and condition C, because again, they're the same people. And you can see here that person number 1 tends to score relatively low across all 3 conditions, even though he or she is maybe showing some sort of a treatment effect. Her scores are declining at least a little bit over time. Person number 5 has relatively high scores. Person number 4 even more so, and his or her scores, person number 4, tend to be relatively high, even though he or she is showing an effective treatment, from let's say A to B to C, or pre-treatment to post-treatment to follow-up. Again, the important idea is that there's a correlation we would expect between these conditions, and we expect that differences that show up between the conditions should be due to differences in treatment, what we did. That is to say, between score A and score B, everyone underwent treatment for depression, or everyone took a particular medication. We expect, or we hope, that those differences we see will be due to differences in our treatment, rather than just differences in how correlated these conditions are with each other. It would be a problem if, for some reason, scores in condition A and B were much more correlated than were scores between condition B and condition C. It would be a problem if the scores between score A and score C were very highly correlated, but the correlation of scores A and score B were not very highly correlated. The problem being that it would be harder to interpret differences across those different conditions as reflective of differences of treatment. Those differences could be influenced in part by how correlated or uncorrelated the different conditions are. Now, that may be hard to visualize, or just hearing me describe it, so bear with me and I'll try to make it a little bit easier for you. So here's some data that I made, and here are the off-diagonal elements in my population variance and covariance matrix. And you can see that these covariances are more or less the same. And here what I've done is I've plotted a separate line for each person in the data set, person 1, 2, 3, 4, and 5, based on his or her score in condition A and condition B and condition C. And I'm argue that it makes sense to test differences between the means across these conditions, since the pattern of relationships across them is fairly consistent. What I mean by that is, generally speaking, although it's not true for every single person, people's scores tend to be declining by about as much across each of these intervals, A to B, B to C, or even A to C. There's kind of a roughly consistent relationship. You can see that in the sense that most people, most of these lines are declining by about as much as every other line. That's the idea of a kind of a consistent relationship across the different conditions. So one way to think about this is you can treat the 3 outcome variables, the scores, as if they really were just one variable, call it score. That is, you can use the univariate approach to this data analysis. If it is the case that these covariances are roughly the same as one another. And by the way, this is why when researchers do repeated measures ANOVA, they often phrase their effects in this way. They treat their different outcome variables as if they were levels of one outcome variable, so one dependent factor, and they'll give it a name like time or dose or emotion. You could imagine that there's a study where emotion or condition A is a positive emotion, condition B is neutral emotion, and condition C is negative emotion, that people are seeing, that people are being manipulated, they're seeing images on a computer screen in these 3 different conditions. But when you do the analyses, because you're pursuing this sort of univariate approach, you call A, B, and C, which are really 3 separate variables, however, whatever it is you're measuring, you call them all one variable, emotion, because you're imagining that there's some sort of consistent effect across all 3 levels. You can imagine here the y-axis is something like level of psychophysiological response, and condition A is positive emotions, condition B is neutral emotions, and condition C is negative emotions. And sort of as we progress across these different levels. People's galvanic skin response is declining, or their heart rate is decelerating, or so on. Anyway, that's sort of the essence of the univariate approach, and it really depends again on this idea of a consistent relationship across the levels of our outcome variable, or our dependent factor, however you want to name it. Now here is some data, or I should say a matrix for some data which is similar to the data that I showed before, except I've deliberately made it the case that the covariances between the different conditions are quite different. So you can see that there's a relatively larger covariance between condition A and condition C than there is between condition B and condition C. And if you were to make a graph, as I did before, plotting each person's response, whatever the variable is, or whatever our outcome variable is, across condition A and condition B and condition C, you could see that there's some significant differences. There's not a consistent relationship here. For some people, their scores are kind of going up and then going down, and then for some people, their scores are going down and then going up, and it's not quite as clean or coherent a picture or consistent a picture as was the case in our previous example. What we're seeing here, if we look very closely, is that there's a fairly high correlation between condition A and condition C, which is to say, generally speaking, your scores on condition A are declining between condition A and condition C. The correlation or the covariation between condition B and condition C is less clear. For some people their scores are going up, and for some people their scores are going down. You can think about this in the sense of, if you knew someone's score at condition A, how well would you be able to predict their score at condition C? Fairly well, let's say. If you knew someone's score at condition B, how well would you be able to predict their score at condition C? Not so well. I did my best to make this data illustrative of this point. You can see here that really it's this one person, person number 1, let's say, in the light yellow line, who's really kind of screwing things up for us. If I'd taken more time, I'm sure I could have made a more disrupted looking data set. But my goal was really to create data where the mean level of the outcome variable at condition A and condition B and condition C was about the same as my previous example, but the covariances between those conditions were very different. So within those constraints, that was the best I could do. And I hope it kind of illustrates this idea that if we had a matrix where the covariances were very different from one another, what that would correspond to is this kind of inconsistency in relationship across the different the different levels of the outcome variable. So again, one way to think about this is you can't treat these 3 outcome variables as if they really were one variable. You can't use the univariate approach, at least not without a bunch of qualifications, if you had a situation like this. And this is why when there are violations of the assumption of compound symmetry, researchers often use a modified version of the F-test. They use one of the corrections that SPSS offers, or they get much more restrictive in the comparisons they make. So instead of considering an overall effect that occurs across condition A to B to C, they might only consider a comparison of condition A and condition C, or they sort of restrict the data that they're looking at, or they could even entirely abandon this univariate approach and say, we're going to use the multivariate approach. We're going to treat scores on condition A and condition B and condition C as entirely distinct from one another, and within the multivariate approach, variables can be correlated with each other or cannot. In a sense, ANOVA doesn't care, or ANOVA is built so as to accommodate situations in which there's very poor compound symmetry. Okay, and an important point to make here, and I haven't really made it yet, is that this idea of compound symmetry only makes sense when there are more than 2 levels of a factor. That is to say, when there are more than 2 conditions. So in our example previously, we had condition A, condition B, condition C, obviously 3 levels. it makes sense, indeed it is possible, to think about the compound symmetry of a matrix of variances and covariances. If we only had two conditions, A and B, A and C, B and C, we wouldn't need to worry about compound symmetry. Indeed, we couldn't really make compound symmetry. That matrix would only have 4 elements, two variances and 2 covariances, but really the 2 covariances are the same. Covariance of condition A and condition B is the same as covariance of condition B and condition A, so we wouldn't need to worry about compound symmetry. Again, this is why if you're a researcher in a situation where you had a violation of compound symmetry, you might think to yourself, well, I can't really use all 3 of these levels, all 3 of these conditions. I'm going to restrict my consideration to just 2 of them, because then it gets me out of this problem of having an inconsistent relationship, an inconsistent or poor compound symmetry for these different levels. So again, here's some data with mild violations of the assumption of compound symmetry, but a very strict researcher who was really committed to using the univariate approach would want to proceed somewhat cautiously. And indeed, he or she could de-emphasize testing the overall effect of the dependent factor and instead just look at a comparison between, say, condition B and condition C, assuming that that was something that makes sense, since that comparison only involves 2 levels of comparison. It would kind of simplify the picture, and assuming that there's a meaningful question that can be answered by comparing condition B and condition C, that might make sense and might get the researcher out of his or her problem with mildly violated compound symmetry. Okay, compound symmetry again is complicated. It can be a bit confusing, and honestly I was surprised and a little bit frustrated when I went to the resources I have to look for good explanations or characterizations of how it works that don't depend on a ton of math. So hopefully this presentation so far has been kind of successful. If not, well, at the very least, please let me know. Maybe there's some way I can explain it more clearly. Moving on, let's talk about sphericity. Now, sphericity is typically described as a more general form of compound symmetry, or a less restrictive sort of quality than compound symmetry. The important idea is that the important point to make is that it is a very similar idea. In the case of sphericity, what we're assuming is that the variances of the differences between our different conditions are going to be roughly the same. They're going to be exactly the same in the population, but roughly the same in our sample. Now, what's important about that is it kind of gets at a similar idea. It gets at that idea that the relationship between condition 1 and condition 2 should be similar to or consistent with the relationship between condition 2 and condition 3, and the relationship between condition 1 and condition 3. So compound symmetry in a way was this more more formal, more specific and fussy way of thinking about that involved variances and covariances. Sphericity is a kind of somewhat looser way of thinking about that, where we instead focus on differences between conditions and then ask, what's the variance of the difference? If you took everyone's score for condition 1 and subtracted it from his or her score at condition 2, and then said, what's the variance of those resulting different scores? And you took everyone's score in condition 3 and subtracted it from condition 1, and you said, well, what's the variance of those different scores? Would those variances be similar to one another? Here is the same data that I've used before, and you can see here we just made some different scores between the scores that people have for each of these different conditions, and looked at the variances, and you can see that the variance of the difference between A and B is not that similar to the variance of the difference between A and C and between B and C. However, the variance of the difference between between A and C is the same exactly as the variance between B and C. Sometimes that's called local sphericity. And what that means is, again, the relationship between A and C is somewhat consistent, or with a relationship between B and C, the relationship between A and B not that consistent with either of those other two relationships. Again, it's that same idea of trying to describe or think about the consistency in relationships of our variables across different levels of our scores, across different levels of this outcome variable. Now here, just to be clear, we have a violation of this assumption of sphericity, but it's probably not too severe because again, it's fairly close and there's at least some local sphericity. Once again, there's this important point that sphericity only makes sense when there are more than two levels of a factor, or more than two conditions. Otherwise, you don't need to worry about it. You know, like these kids, you can be like, woohoo, we don't need to worry about sphericity, or indeed about compound symmetry. As a side point, I have one stats textbook that I've used in the past where the authors argue that essentially you should always do you should always do analyses for dependent designs based on comparisons of two and only two levels of your dependent factor. That is, you should only ever be comparing, condition A versus condition B, or condition B versus condition C. You should never, or at least you should avoid, making some sort of more general statement about A versus B versus C, because they think that this whole world of sphericity and compound symmetry is too easy to get confused about, which you may well agree with that point, but anyway, moving on. Here's our data one more time, and you can see that I've computed the variances of the differences to think about sphericity, and also the variance covariance matrix to think about compound symmetry. And in the case of compound symmetry, the variances are different, so are the covariances. In the case of sphericity, the variances of the differences are close. You kind of can see, if you really sort of squint at this, these tables or matrices, that really what's interesting here potentially is that the relationship between condition 1 and 3 and 2 and 3 is fairly consistent, but it's the relationship between condition 1 and condition 2 that's somewhat inconsistent with the others. So whether you think about that in terms of variance of differences, or if you think about it in terms of covariances across these different conditions, you kind of get a somewhat similar picture. And indeed, compound symmetry and sphericity, they're getting at that same idea. Now, you'd be forgiven if you didn't want to bother to make a table of variances of differences, or a matrix of covariances and variances every time you did a repeated measures ANOVA, because it's a lot of work, and ultimately it's not like there's a precise rule where how much of a difference is too much of a difference. Although I would encourage you to try this at least once or twice. It's not that hard to do, and it does give you kind of a sense of what your data kind of looks like, and that can be valuable. However, if you're working in SPSS, or probably in other stats programs as well, you automatically get Mauchly's test of sphericity. What Mauchly's test does is it tests a significance, or it tests the hypothesis that the variances of those differences are all equal. And so thus, like other tests of assumptions, significant results for this test suggest that the differences between the conditions are different in their variances. That is, that sphericity has been violated, or the assumption of sphericity has been violated. Non-significant test results suggest equality. That your assumption of sphericity has not been violated. An important point to make is that like pretty much all other tests of assumptions, if you have a very large sample of data, if you have many people who are going through your repeated measures ANOVA, then very small differences in the variances of the differences between those conditions can be significant. And if you have a very small sample, as you sometimes do if you're doing a repeated measures design or repeated measures ANOVA for a dependent design, then very large differences in the variances between the differences can be non-significant. These tests, whether it's the Kolmogorov-Smirnov or the Spiro-Wilks or the Mauchly's test or Levine's test, they're nice because they help us think about something complicated, and they give us rules for deciding when, how much of a violation is too much of a violation. But they're limited in the sense that they work best in situations where we don't need them very much. That is, when we have very large samples, and they work poorly in situations where we kind of need them more, that is, in very small samples. So you have to be a little bit circumspect in thinking about them. Let's imagine that you're doing an analysis in SPSS. You're using a univariate approach to your dependent design. You're doing a kind of old school or classic repeated measures ANOVA. You get automatically Mauchly's test, which, by the way, you would only get, or it would only be interpretable if you had more than 2 levels, if you had 3 conditions or 4 or 5, etc. So you get Mauchly's test, and it suggests, and it's p less than 0.05, suggesting that the variances of the differences between the different conditions differ from each other, that you've violated the assumption of sphericity. Well, first off, it's worth saying this is likely to happen. I mean, there's a reason why at least some researchers don't like repeated measures ANOVA, because you almost always violate the assumption of sphericity, or indeed the assumption of compound symmetry, if you were to go to all the work to kind of create a matrix and kind of squint at it and think about it. It almost always is the case that the relationships between condition A, condition B, condition C, condition D, and so on are not consistent enough to really treat these scores for all of these separate conditions as if they were scores for one big outcome variable. But while it's true to say that there's almost always a violation, it's not almost always a disaster. What it usually means is that the F statistic will lose power. Your repeated measures ANOVA will have a poorer time, or be less able to detect significant effects, at least across the full range of levels of your dependent factor or your outcome variable. Again, this is why a savvy researcher might think, I've violated the assumption of sphericity, I've violated this assumption of compound symmetry, it doesn't look good, my matrix doesn't look symmetrical. What I think I want to do is not so much focus on all the levels of my outcome variable, but maybe confine myself to just looking at two-way, or I'm not two-way, but two-level comparisons, comparing condition A to condition B, or condition B to condition C, or A to C, or whatever, not trying to compare all the levels to each other. Another option that the researcher might have would be to use one of the many corrections for the F statistic that SPSS provides, so as to kind of shore it up, or kind of reinforce it against its loss in power. Now, you don't need to know how all these corrections work. I don't frankly know how they all work, or at least I haven't ever bothered to look into it that deeply. But it's worth noticing that what they do is they basically fiddle with the degrees of freedom used in the numerator and denominator of the F equation. The numerator degrees of freedom and the denominator degrees of freedom, so as to make the test somewhat more robust to this violation of assumption of sphericity, make it somewhat less likely to lose power. Now, the two that we focused on in class are the Greenhouse-Geyser correction and the Hundfelt correction. I hope I'm pronouncing it correctly. The only really important thing for us to know is that the former is relatively more conservative, meaning it provides less, it doesn't work as hard to bulk up the power of F, because of course, if it really overpowered F, you could get into a situation of having false positives. And the Hundfelt is somewhat more liberal. So one gives you relatively more help against potential loss of power, the other gives you relatively less. It's up to you as the researcher to try and decide which makes more sense. I know, or at least I've seen some researchers who will just average the two and use that, or which is to say average the p-value for the two of the correction using Greenhouse-Geyser and the p-value for the correction using Hundfelt, and take that average as the probability value to then compare to 0.05. That's just one kind of informal way I've seen people do it. So all of that stuff that we've talked about so far is all concerning the univariate approach to dependent designs, or what we sometimes call the classic kind of repeated measures ANOVA approach. Now let's focus on the multivariate approach. What assumptions do we need to make for that approach? Well, the multivariate analysis of variance, or MANOVA, treats the multiple outcome variables as a single set, which is to say not as one variable, but rather a set of variables, because of course they are a set of variables. Scores in condition A and scores in condition B and scores in condition C are not all just scores of one big outcome variable. They're scores for 3 little or separate outcome variables. And in a sense, each participant gets his or her own set of values. So rather than trying to predict one score per person, we're trying to use a model that predicts a set of scores, or I think technically a vector, an array that has 3 or 4 or 5 elements. So again, rather than each person has one and only one outcome variable, now each person has 3 or 4 or 5 or however many you have. What's important for us right now is to note, as I think I already have, that MANOVA does not assume compound symmetry or sphericity. It allows that these variables may be correlated, they may be uncorrelated, the correlations between different pairs of them may be different from one another. MANOVA just kind of doesn't care. And there are lively debates, as lively as statistics debates can get, I suppose, as to whether repeated measures ANOVA, the univariate approach, is better or worse than MANOVA, that is, the multivariate approach. And as is often the case, the answer to this is kind of like, it depends. If you had a situation in which you only had 2 levels of an outcome variable, then repeated measures ANOVA is fine. In fact, it probably has better power than MANOVA for that comparison. If you had a situation in which you had 3 or more levels of an outcome variable or a dependent factor, repeated measures ANOVA, the univariate approach, may do just fine if the assumptions of compound symmetry and sphericity are met, or at least they're almost or mostly met. If you had a situation in which there were big violations of that assumption of compound symmetry, or relatedly of sphericity, then we might expect that repeated measures ANOVA, the univariate approach, would have relatively less power, or would just be tricky to interpret as compared to the multivariate approach, the MANOVA approach. So to be clear, the MANOVA thing, the multivariate thing, is beyond the scope of this class. It's not something that I'm going to spend really much more time, or really any time, talking about, but I just wanted you to have some awareness of the distinction between the two. Well, like I always say, thank you so much for your attention. Compound symmetry and sphericity are tricky concepts. They can be confusing to think about. I hope that this video helps you a little bit with that, and as always, if it does, great. If it doesn't, please let me know. I'll try to explain it in ways that make more sense to you. So again, thanks so much. Bye-bye.